All right. Hello, everyone. My name is Vitaly Podzarov, and let me share the screen first. Share. Okay, so let's start from the beginning. All right. So today I wanted to tell you about our high-resolution IC Hall effect measurements of organic semiconductors that allowed us to understand the charge transport properties of these materials much better. So here, by the way, in this photograph, you can see this beautiful red crystal. It's a rubrine single crystal with an FET field effect transistor structure deposited on its surface, wired to the sample holder for measurements. So rubrine is the highest performance organic semiconductor today, and it's our favorite system. We use it a lot, study it a lot, and it's like a fruit fly of charge transport studies in organic electronics. All right, so this slide is a very simple introductory slide showing the essence of the Hall effect measurements for those who are not particularly involved in this topic. You might have heard that the first original Hall effect measurements in organic semiconductors were performed in high performance rubrine single crystal OFETs described in these papers. So what is done here is the following. So we run current in the longitudinal direction between the source and drain. So the carriers are flowing, drifting in this horizontal direction, and the magnetic field is applied perpendicular to the channel. Okay, and in these conditions, there is a Lorentz force acting on the charge carriers sideways, causing their trajectories to bend towards one side of the channel. And this leads to the formation of the Hall voltage in the transverse direction across the channel. And this is what we measure, this V Hall, okay, shown here, for instance, in this original experiment by this black data points. The importance of the Hall effect measurements in organic semiconductors, the main importance comes from the fact that they can be used to distinguish the band transport from incoherent hopping transport. Because in the band transport, one can introduce microscopic velocity of the carrier, this V, and therefore the classical Lorentz force is going to be non-zero, and you'll see the effect. While in the hopping regime, the carriers are moving by quantum mechanical tunneling from molecule to molecule, okay? And in this regime, even though you may have a non-zero net current flow in a certain direction, microscopically, the velocity is, well, it cannot be defined. So it's essentially zero. Instead of the velocity, you have probabilities of tunneling between the molecules. And so the classical Lorentz force is zero. So one should not be able to see any classical Hall effect, at least in the hopping transport regime. So merely an observation of a classical semiconductor like Hall effect in organic system is a good smoking gun proof that the charge carriers indeed can be delocalized and the transport is band-like. Also, as this discussion suggests, the charge carrier mobility that you extract from Hall effect measurements gives you the mobility, the trap-free mobility of band carrier, because Hall effect primarily probes the charge carriers that are instantaneously mobile. Okay, because only the Lorentz force is acting only on those carriers. Well, this statement is not true in 100% of cases, because hopping carriers can partially screen Hall effect, but in many systems, the Hall mobility is indeed very close to the intrinsic band, trap-free band mobility of charge carrier. So it gives you the upper limit for the performance of the system in terms of its carrier mobility. Now, the trouble is that the Hall effect measurements in organic semiconductors are very difficult to perform. And this is primarily due to the fact that this signal to noise ratio is very poor in most of the cases, even in the case of very high mobility organic semiconductors. So the reason for that is that the mobilities are usually very low, much lower than in inorganic counterparts, which means that we expect to see much smaller Hall voltage signals. On the other hand, you still have, even in the purest crystals, you have some residual traps that trap and detrap charge carriers, and this kind of multiple trap and trap and release processes, they cause fluctuations and noise. So the mobilities are low, noise is high, so we have this problem of signal to noise ratio as a result. You can see this slide shows some examples of measurements by other groups in other systems. You can see that the noise is usually pretty bad, even though in these examples people are using very high magnetic fields, 6 Tesla, 10 Tesla, 10 Teslas, 6 Teslas. So in order to solve this problem of signal to noise ratio, we have recently introduced this high resolution AC Hall methodology for Hall effect measurements, which is basically using a well-known concept of phase sensitive detection using lock-in amplifier. So here, instead of applying a DC magnetic field, we're applying an AC low frequency magnetic field, and we detect the Hall voltage by a lock-in amplifier tuned exactly into this frequency. So this technique dramatically improves our signal to noise ratio. In our setup, the AC magnetic field is created by by the mechanical rotation of assembly of permanent magnets, shown schematically here. And this is the photograph. This flat piece here is actually a vacuum chamber with the sample sitting inside, right? So the sample here, it sees an oscillating magnetic field as this frame rotates. So this system has boosted our signal to noise ratio dramatically, and now we can study a huge variety of low mobility systems in our lab. Some of them are listed here. They include small molecules, polymers, hybrid perovskites, different network materials like MOFs, monolayer materials, inorganic oxides, including amorphous oxides. So some of the good features of these system involve are listed here. So besides the boosted signal to noise ratio, it uses a small magnetic field produced by these permanent magnets, less than 1/4 of a Tesla. Very importantly, it does not need any superconducting magnets, does not require liquid helium, and that's a huge simplification. Okay, so therefore the system is small. It's a desktop convenient apparatus that doesn't require any maintenance. Also, recently we have introduced a bunch of updates to it. Now we have an option for temperature variable measurements. We have an option of in situ photo excitation, for instance, for photo Hall effect measurements. We can also do strain variable measurements in situ at the same time measuring Hall effect, and so on. Also, this system, of course, is good not only for low mu systems, but you can simply measure, also measure gallium arsenide or graphene high mobility systems. So overall, very convenient. Here on this slide, I'm showing a couple of examples of the use of this technique in organic transistors. Here on the left, we have high performance single crystalline rubrine transistors. You can see that these devices perform very nicely, exhibiting a textbook performance, very nice linear characteristics in the linear regime, perfectly parabolic characteristics in the saturation regime. Also, mobility measured by different approaches, 2-probe, 4-probe measurements, Hall effect, Hall effect shown here by these dots. All these mobilities match, and they are carrier density independent here. Also, if you look at the carrier density, you'll see that the total carrier density, which is this capacitively defined carrier density shown by the solid line, matches very well the carrier density measured by the Hall effect, indicated by these dots. This situation, when the Hall measurements in terms of the mobility and carrier density match very well FET measurements, we call this situation a fully developed Hall effect, which suggests that 100% of your charge carriers in the system are delocalized and mobile. So they're fully band-like system. Here on the right, we have a little bit of a different example. These are much lower performing single crystal tetrazine transistors. You can see that these devices have much lower overall level of mobility below unity. Nevertheless, this high resolution AC Hall technique allowed us to resolve successfully Hall effect in the system. And surprisingly, the Hall effect measurements in this system show that the Hall effect matches the field effect measurements. So you can see the mobility is roughly matching the longitudinal mobility, and the carrier density is roughly matching the capacitively defined carrier density. So initially, at the time of this measurement, it was a mystery. How can that be in the system with such a low mobility? The reason this is a mystery because it was believed that organic semiconductors with mobility lower than 1, they cannot be in a band-like mode. They should exhibit a hopping type of transport. And if that was the case, then how could we see a Hall effect in the system, and especially fully band-like Hall effect, fully developed Hall effect? So this was one of the mysteries of the Hall effect at that time, and we were actually able to resolve it with a model that is summarized here. I will not spend too much time on this model here because I wanted to switch gears and talk about newer measurements, but let me just briefly mention this here. So the essence of this model is based on the notion, this notion of thermal disorder that we learn from our gurus, Alessandro Troisi and Simone Frattini, who told us that in organic semiconductors, even in the best ones, where you don't have any static disorder, in the most pure cases, you still have off-diagonal thermal disorder due to the thermal motion of the molecules. And this type of disorder creates this tail states. Usually it's an exponential tail of localized states that are significant in these systems. And so also there is a band, the band of states here, these delocalized states. So when you pour in the charge carriers into such a system, you feel all the states, up to a certain level, usually somewhere in the vicinity of the mobility edge. And so you would have both type of carriers in your system. You would have carriers that exist in the band that are moving as band-like, at least a fraction of their lifetime. And also you would have hopping carriers that are moving within the tail, within these localized states. So here in this cartoon, I'm showing this situation by these two dots. So this red dot represents a band-like carrier that is moving in the band, which experiences both the electric forces and the Lorentz force under Hall effect measurement conditions. This blue open circle represents a hopping carrier that is moving in the tail, in the localized states. So the hopping carriers, they do not experience Lorentz force. They only experience electrostatic forces. And so the band-like carriers are mainly responsible for the formation of this transverse Hall electric field And this electric field is pushing the hopping carriers in the opposite direction. And so they compete with the band-like carriers in creating the whole voltage. So essentially, they partially compensate or screen this whole electric field. Now, when you work out the details of the model requiring that in the steady state, the transverse current density, JY, should be 0. So if you analyze this model in details, you will see that it actually successfully captures main features of Hall effect in disordered organic semiconductors, including it actually explains some of the mysteries, including this one in tetrazine. So this model shows that there is a large parameter space. Here it is shown by this yellowish orangish area, where you might be very far away from the fully band-like transport regime. Nevertheless, the Hall effect mobility and longitudinal FET mobility will be very close to each other, within 10%. For instance, if you're within this droplet of parameters here, your diffraction of the band carriers in your system can be rather small, only 30%, and the rest of them are hopping. Nevertheless, here the Hall effect measurements would be almost indistinguishable from the longitudinal measurements, and that seems to be the case in this system in tetrazine. So, in order to really tell apart these two situations, the one like in tetrazine and the truly band-like system, such as in rubrine, one needs to do more measurements, other measurements, including, for instance, the temperature dependence of the carrier mobility. Also, another a mystery that this model explains is this observation made by Takeya's group that apparently in pentacene, carrier density measured by Hall effect is almost twice greater than the capacitively defined total carrier density. So this result seems to be absurd, okay, but this is true, of course. This is what measurement shows, and the reason you have this seemingly absurd result is simply because this conventional formula for the Hall effect is used to determine this Hall carrier density and Hall from the measured Hall voltage. The problem is that this formula is only applicable to the case of a purely band semiconductors, where 100% of your carriers are band carriers, the localized band carriers. But in this case, because disorder is high, there are a lot of hopping carriers that are screening your Hall voltage. So the Hall voltage is reduced, and therefore you get overestimated Hall carrier density. So this is very well explained by our model. Finally, another mystery is something that was measured in Henning-Sellinghaus group. So here they measured Hall effect in these two systems, TIPS pentacene and TMTS pentacene. And you can see that here in TIPS pentacene, shown by blue data points, the Hall carrier density, well, the situation is very similar to the pentacene. The Hall effect carrier density seems to be much greater than the capacitively defined carrier density, indicating that the Hall effect should be only partially coherent. On the other hand, in this TMTS system shown by red data points, looks like there is a match between the Hall and capacitively defined carrier density, which suggests that Hall effect is 100% coherent. Nevertheless, when you look at the temperature dependencies of the carrier mobility, you can see that the TMTS system is farther away from being from exhibiting this band-like region of the temperature dependence. So there is a kind of an apparent inconsistency between these two pieces of measurements. And of course, the data are correct, everything is fine, and you know how to explain it, it's actually explained in our model here. The explanation is based on the fact that hopping contribution of hopping carriers is different in these two systems. In the one case, you have strong hopping contribution. In the other case, you have intermediate hopping contribution. Okay, so I will not go to the details of this. So for those who are interested, please look up this paper, and there is a model that explains all this. Okay, so now let me switch gears to some of our newer measurements. In particular here, I wanted to describe our measurements of the intrinsic mobility-strain relationship in organic semiconductors. By the word intrinsic, I mean the reversible changes in the charge carrier mobility, in the intrinsic charge carrier mobility, which is the mobility not dominated by static disorder, caused by elastic lattice deformations by strain. So to do these measurements, we have fabricated this flexible organic single crystalline devices based on ultra-thin rubrine single crystals laminated on these flexible substrates with contacts. Then we coat these samples with a layer of parylene, shown here in bright blue, and they are topped with the gate. So you can see here the contact geometry we use is the 4 probe and whole bar, so that we can do 4 probe measurements to address possible contact effects, and we can apply calibrated uniaxial strain in essentially any axis within this AB plane. So our notation that we use is the B axis is the direction along the molecular slip stack. It's a high mobility axis of rubrine, and A axis is the one perpendicular to it, so the low mobility axis. To apply strain, we use this custom designed miniature strain stage where you have this micrometric screw, a calibrated screw, and the substrate can be clamped here between these parts, and you can bend it by using the screw like this or like that. So essentially what we're doing in these measurements is the simultaneous Hall and FET measurements as a function of calibrated mechanical strain applied either along the transport direction, the high mobility direction, or perpendicular to it. Okay, so this slide shows the main results. So the upper panel here shows the charge carrier mobility in these transistors as a function of strain, strain in percent epsilon. The negative values correspond to the compressive strain, and the positive values correspond to the tensile strain. In our devices, the transport direction is along the high mobility B axis, okay? And the strain is applied either in this direction or perpendicular one. So the red and blue data points correspond to the Hall mobility and the FET mobility. And you can see that there's a large, actually, anisotropy of the effect. When the strain is along this high mobility transport direction, you can see a large modulation shown here by this red and blue data points. And by the way, you can see that overall the Hall mobility is relatively close to the longitudinal mobility, which means that the samples we're using, they're very close to being fully bend-like trap-free crystals. On the other hand, when you apply strain in the transverse direction, which is shown here by this darker data points, there's almost no effect on the mobility. Okay, so the lower panel here is essentially the same data set. It's just here the vertical axis is the relative mobility change, delta mu divided by the unstrained mobility value mu naught. Okay, so yeah, and in this strain along the transport direction regime, you can calculate that the effect of strain is pretty significant. It calculates to about 70% of increase in the mobility at 1% of compressive strain, and it's quite symmetric. There is a little bit of a plateau region, or maybe you can call it like threshold-like region in the middle for very small values of strain. And we believe that this is some sort of a technical device artifact, probably because at very small initial values of bending, the elastomer is absorbing part of the strain, is accommodating it without really transmitting it into the crystal. So, but that's okay, we can live with that, because above these values, strain picks up and the effect picks up, and we can see a quasi-linear relationship between the mobility and strain. So, well, the reason I'm insisting that this is an intrinsic structure property relationship in terms of the strain is that the Hall effect measurements in this work they're performed for the first time as a function of strain. And as you know, Hall effect really looks into the intrinsic transport. Okay, so to be fair, I have to mention that we're not the first ones who are trying to address this important experimental problem. There are a few papers where people have tried to do that. For instance, Bresenio's group in this paper used rubrene in their, famous wrinkling experiment. Also, there is a Batlog's preprint. It's published online on archive. Also, there is a paper by Michaela Mata and co-workers published in this journal. These are very nice early experimental attempts to to address this apparently very difficult problem of mobility strain relationship, yielding some interesting initial results. But unfortunately, we cannot really make a thorough comparison of their data with ours, because there are a few experimental deficiencies in these works that I briefly mentioned here. So first of all, everything in these papers is done by two-probe, and therefore contact effects are unaddressed. And this is bad, because we know from Frisbee's work, for instance, that was published in this paper, that contact resistance can be strain dependent, and therefore contact effects could have a important impact on your two-probe mobility. Also, no measurements were done at compressive strains applied along the transport direction, at least in these two papers, number 2, number 3. And this is very strange, because it seems that applying compressive strain and measuring the mobility is the most interesting thing in this whole business. And that simply means that a big chunk of data, important data, are simply missing here. It's not missing in Bresenio's group, but the problem with their measurements is that it's very hard to interpret wrinkling. It's very hard to extract strain values from the wrinkled structure. They had to use some extensive modeling to obtain the actual strain in the wrinkling, because they are not using simple bending. They use wrinkling. Finally, the strain effects observed in these works, strain effects are observed in a very narrow range of parameters. So for instance, here, if I overlay Mata's results here on our results, you will see this. So all of their data points are within 0.15%. So in this very small subthreshold region, so-called subthreshold in our case. And these bright circles here show the maximum values of their strain effects. So it's all here. It's basically, in our perspective, it's kind of indistinguishable from our noise and scatter. So for that reason, we cannot say that their measurements are inconsistent with ours. They're simply too limited to be, to be useful for such a comparison. Also, I would like to mention that there is already a pretty substantial body of theoretical efforts in this direction to describe this mobility strain relationship in rubrene. Well, I know of these 4 papers, particularly David Bell-Jones' paper, Gabriele and Simone's paper, also the paper from Alessandro Troisi, and this very recent paper from Johan's group. Unfortunately, we don't have a good agreement between our experimental data and these theoretical predictions. While our work seems to suggest that this mobility strain effects in rubrine are kind of intuitively simple. They make sense in terms of looking at the molecular packing in rubrine. But these theoretical works, they predict rather complex, non-intuitively simple behavior. And honestly, we don't understand why there is such a disagreement between our experiment and theory. It is possible that there is some important ingredient in this theory which is missing that leads to this disagreement. Also, it is possible that we don't understand something serious about our experimental procedures, about our measurements, although at the moment I cannot think what could be wrong in our experiment, because we seem to approach this problem from multiple experimental perspectives, and we took care of many things. So, well, currently the state of this subfield is basically that mobility strain relationship is still an open question. And this is not bad, because this basically makes our life less boring. This indicates that we didn't understand everything yet. So we're planning more measurements, and I hope that theoretical efforts in this direction will also continue. So finally, let me switch gears again and talk about Hall effect measurements in polycrystalline transistors, elucidating the role of grain boundaries in charge transport and Hall effect. So in this project, we collaborated with Antopoulos group, who are growing this nice films based on blends of small molecules, C8-BT-BT, with conjugated polymers. Sometimes they dope them with the C60-like molecules for an improved performance. So what happens in these blends is that the small molecule film segregates on top and crystallizes, forming these nice polycrystalline films. And we top them with a gate insulator and a gate, and producing these top-gated transistors and measure charge transport and Hall effect. We also collaborated with Barry Wren's group at Princeton. So Barry's group, they are growing absolutely magnificent polycrystalline rubrine thin films. So these films are very beautiful. They have a huge grain size, up to 0.5 millimeter or even 1 millimeter. They can be a very large area, inch by inch. They are uniform. They are pinhole-free, compact. Visually, they are transparent because they are extremely thin, about 50 nanometer in thickness. What's important is that their performance, if you build the devices, the FAT devices on them, their performance approaches performance of single crystalline rubrine. So they are very high quality, high performing films. From practical perspective, they're very important because these are not solution grown. These are evaporated in high vacuum and with some post evaporation annealing. But the reason it is important is because it's very easy to achieve patterning of these films. In this case, you can just deposit through shadow mask and patterning is done. Unlike solution processing methods where patterning is a pain in the neck. Also, fundamentally, these films are very interesting because the grain size in these samples is so large, and the grain boundaries are so well defined that you can have an individual single grain or just a few grains in your macroscopic semiconducting channel in your device. Here, for instance, you can see this is an actual polarized optical microscopy image of one of our devices where you have source and drain, voltage probes, and you have a few grains here growing from this point. And what you can do, you can, by using optical microscopy, you can polarized optical microscopy, you can determine the crystallographic orientation of individual grains. And therefore you can determine the type of grain boundary, so the grain boundary angle that you have in your channel. And so you can study the the effect of this specific grain boundaries on the transport or Hall effect in your device. And so this is what we were doing in this paper. And here I wanted to show you one specific interesting result. It's about the role of grain boundaries and Hall effect. So here the observation was that these polycrystalline transistors perform very nicely. You can see very nice linear characteristics in the linear regime. And the longitudinal fat mobility is very, very good. It's up to 6. 6 is about some of the best results we were getting in the with these devices. So it indicates that these are high performance transistors, but every time we measured Hall effect in these polycrystalline transistors, we obtained values that are significantly lower for the Hall mobility. For instance, in this example, it's 3 times lower than the longitudinal mobility. And respectively, the Hall carrier density was hugely overestimated. It was 3 times greater than the total carrier density. So this kind of a disagreement between longitudinal and Hall mobilities cannot be explained by that model that I was talking about at the beginning, because that model says that at this high level of longitudinal mobility, about 6, the system should be almost completely coherent. So almost 100% of carriers should be delocalized and moving as band-like carriers. So there will be too little of a fraction of hopping carriers in this case to account for such a huge difference, for such a strongly underdeveloped Hall effect. And therefore we start thinking about possible other mechanisms, and we were thinking about grain boundaries. And it turns out something here can explain this behavior. So this cartoon on top schematically depicts the conducting channel. So the longitudinal direction here is the vertical direction. So current is flowing vertically. These 2 dots are the Hall voltage probes, and the magnetic field is perpendicular to the plane. So each grain can be thought of as a single crystal with a charge transport which is fully coherent within. But each grain is misaligned with respect to the vertical transport direction. And there is a natural charge transport and anisotropy in most of the organic system. And therefore the longitudinal mobility, this what I call here mu x, is different in each grain because they are rotated, they are misaligned with respect to each other. But what determines the Lorentz force and the Hall voltage EMF, the Hall effect EMF in each grain, electromotive force, is actually this longitudinal mobility mu x. Ex, which is source drain electric field, is the same for each grain. Mu x is different. But if you remember, to balance, to solve this Hall effect steady state condition in this Hall measurements, one needs to balance Lorentz force with the transverse electric field, the electric field that is along this direction. So in the case of a homogeneous channel, it's easy to balance it because you have one Lorentz force in your channel, and you have single value of the transverse electric field produced by the charge carriers that are accumulated at the edges of the homogeneous channel. In this case, however, the task is to balance different Lorentz forces in different grains, and therefore one cannot do it simultaneously in all the grains using only one electric field. So this leads us to the conclusion that in order to achieve a balance here, something between these grains should carry a non-zero charge. And this something, the only thing that this could be is the grain boundary. So this led us to this conclusion that the grain boundaries in these systems under the Hall effect measurement conditions should be capacitively charged, and there must be some very small but non-zero net charge sitting on these grain boundaries. That leads to a partial compensation of the Hall voltage, because as you go across from left to right, or right to left, every time you pass this grain boundary, there will be a little potential drop associated with such a charged grain boundary. And altogether, these drops would cause to screened or reduced Hall voltage. So this is an important understanding of the Hall effect in these polycrystalline devices. Important for practical purposes, because practical means that every time you are going to characterize polycrystalline organic transistors using, for instance, Hall effect measurements, we'll have to keep in mind this effect. Okay, and finally, let me briefly talk about the last topic that I wanted to cover, is the first photo Hall effect measurements that we have performed recently, again in our favorite material, rubrene. Now here, these devices are not transistors. They are not coated with gate dielectric or gate. This is just freestanding transistors with free top surface sitting on a substrate, of course, with contacts in the Hall bar geometry. So in these devices, we are not relying on carrier injection from contacts. We create photocarriers. We excite electrons and holes everywhere in the channel by using uniform illumination. So these electrons and holes that are photogenerated in the channel, they drift in the opposite directions along the channel in the longitudinal direction, and contribute to the photoconductivity and the measured photo Hall voltage here. Okay, I mean, in principle, both electrons and holes should participate in this, and the task is to extract these microscopic parameters, mobility of electrons and mobility of holes, and their carrier concentrations from the experimentally measured photo Hall mobility and photo Hall carrier density. So in order to obtain these parameters from these measured values, we have developed this model and that is described in detail in this paper, including for the case of an anisotropic semiconductor, which is useful for organics because most of the organic crystals are anisotropic. So basically, the model says that if you plot the photo Hall mobility versus the photocarrier density n, actually one can think about this horizontal axis as incident light intensity. Okay, so as you plot this mu photo Hall as this light intensity, initially you have some value, but then it rolls off and shows this kind of flattening, this saturation at high intensities. And the reason this happens is because in the low light condition, or in the dark, you may have some dark carriers, for instance, due to unintentional doping, probably holes, for instance, as in rubrene, or if the system is doped, it would be a certain type of carriers corresponding to doping. But then as you generate more and more photocarriers by photoexcitation, the photocarriers start dominating, and as you know, electrons and holes, they compete for the formation of photo Hall voltage. They work with the opposite sign, and so the mobility here, the photo Hall mobility at the plateau, should be equal to the difference between the electron and hole mobility. So here, this mobility should be equal to delta mu, equals to mu electron minus mu hole. And we have done control measurements in single crystalline silicon. This is n-doped wafers, and we do see this this roll off, although we cannot reach the saturation because it would require too high of a photoexcitation. But nevertheless, when we fit this photohole mobility shown here by black circles with our model, we do extract the correct parameters for the mobility, separate mobility of electrons and holes. So the model works, and now we apply it to rubrene, and we see something that is completely unexpected. So here, this plot shows the photohole mobility measured in high purity rubrene single crystals. It is shown here with black symbols, and you can see that it is flat. It's just flat. There's no roll-off. It's very flat over many orders of magnitude on light intensity. Okay. And by the way, another benefit of the Hall effect is that you can directly check the sign of the dominant charge carriers, and the sign in this case is corresponding to holes. So holes are conducting our photocurrent, and the absence of this roll-off at high intensities can only be interpreted as the absence of electrons. More precisely, it's not the absence, but the electrons appear to be completely trapped at any light intensity within this huge range of values. Okay, so all the electrons that we possibly generate by light, they're trapped. While the holes are mobile and they carry 100% of our photocurrent. Also, in these measurements, we can separately measure the photocarrier density. It is shown here by these red data points, again, as a function of incident light intensity. And you can see this strange power law. This is a double log plot. So this power exponent is 1/4. And in fact, it is consistent with some previous observation. By the way, in some lower quality samples, we see 1/3 also. It depends on the regime. You probably have seen this paper, I hope. This was our earlier study in 2015, where we discovered that photoconductivity in rubrene, when you plot it as a function of power, incident power, it exhibits this very interesting fractional exponents. Well, initially it goes like linear. The power is 1, but then you can see a transition to power 1/3 and eventually to the power 1/4. And the reason this is happening is because of there are processes of triplet exciton singlet fission into triplets, triplet exciton diffusion towards surfaces where triplets are interacting with some defects, producing surface photoconductivity, surface photocarriers. And then there are processes of triplet interaction with the charge carriers, triplet charge quenching, and also triplet fusion. So all this was explained by a model introduced in this paper. And here in this newer photohole study, we seem to confirm this behavior, confirm this fractional power exponents, now using completely different measurement methods, not just photoconductivity, but photohole effect. But the additional twist here is that now I understand that the mechanism of photoconductivity generation is actually triplet exciton interaction with surface defects, electron traps. So the triplet comes up to the surface through diffusion, interacts with apparently with an electron trap. So the electron is trapped and the hole is released. So the mobile hole is moving and carrying the photocurrent in the system. That's the newer understanding of the fundamental mechanism of photoconductivity in this high purity rubrene crystals. So with this, let me conclude by saying that, I hope I was able to show you that AC Hall effect measurements is a powerful methodology. It makes Hall measurements in organic semiconductors relatively easy, much easier than, at least compared to the DC measurements. And we can obviously address a range of fundamental topics, fundamental problems of charge carrier transport and photophysics in organic semiconductors, and also in other low mobility materials by using this methodology. So for those who are interested in details, I would refer you to our webpage, where you can find many interesting pieces of information, including some technical notes. And with this, let me thank my team, specifically those listed here in bold who contributed to the topics that I just covered today: Yanzhen Chen, Hyun-Ho Choi, and Vladimir Bruevich. And also, I'm really lucky to have all these wonderful scientists as my collaborators. Without them, no work would be possible, of course. And specifically for the materials that I presented here, we're very thankful to Barry Rand, Thomas Antopoulos, Jun Takei, and Yuri Garstein for their help and contribution. And also, we're indebted to the National Science Foundation for their support of this work with grants. And so, thank you very much for your attention, and I'm open for questions.